Hello everyone. I'm Gitanjali Jaina. I'm a PhD scholar from IIT Delhi. So I welcome you to the third live section of this course, Introduction to Laser, which is taught by Professor M.R. Sanai. So during each section, we will go through the concept that has been taught during this week or in the previous week, and we will go through the concept as well as we will solve a few problems, few basic as well as few numerical problems that will help you to understand the concept, as well as this will help you to understand the assignment that is being posted in the NPTEL site. And beside this concept, I will also clarify the doubts that you must be having for the assignment. So let's wait for 2-3 minutes, then we'll start the section. So before that, let me ask whether you have any doubts in the previous live section, doubts in concept as well as in the problems that I've solved, or do you have any doubts in the assignment of this week 1 and week 2? The solutions are already being released in the NPTEL site. So you must be knowing this all the solution for these problems. So do you have any doubts in the problem of week 1 and week 2? So you both of you are unmuted, so you can ask the query. Otherwise, you can write it in the chat box also. So if you have any doubts regarding the solution that has been posted in the NPTEL site, so you can write it in a discussion forum, and you can get the answer from the NPTEL team for your doubts, as well as if you are not getting the answer, then I will good evening. So I will solve the problem. I will try to clarify your doubts. Okay. So assignment 1, question 8. Okay. So let me go through the question first. So the question is, uh, let me add it. Assignment 1, question 6. Okay, let me solve the question number 8 first. Then we will go through the question 6. So 8, assignment 1, question 8 and 6. So let me see the question first. Give me some time so that I can go through the question. Assignment 1. So the question number 8 is the energy difference between atomic levels in a non-degenerate two-level system is 1.8 electron volt. So there are two energy levels. Yes. So there are two energy levels, E1 and E2, and it is 1.8 electron volt. If the two-level atomic system is in thermal equilibrium at room temperature, so it's KBT. In thermal equilibrium, the energy must be KBT. So KB value can take 1.38 into 10 to the minus 23, and T is 300 Kelvin. Then ratio of number of atom in the excited state to the ground state. So number of atom in the excited state by number of atom in the ground state, it's directly proportional to E to the minus this will be E2 by KBT, and this one is E2 minus E1 by KBT. So that means this is E to power E1 minus E2 divided by KBT, right? And KBT value, if you find it from here, so you will get around 0. What is my calculator? So KBT, I think 0.25 millielectron volt you will get because it's from temperature. 1.38 into 300. So, okay, so you need to convert this. This is in joule per Kelvin, I think. So you need it, you need to convert it to electron volt or in joule. So if you need, so let's find it. So it is in Kelvin. So let's convert it into electron volt. So if you want to look, so we have to divide it by 1.6 to 10 to the minus 19. I think you will get around 0.02587 electron volt. This is KBT, and E1 by E1 minus E2 is already 1.8. So you will get E to power minus 1.8 divided by 0.02587. So I think so you will get to, what is the answer we are getting in question number 8? So let me calculate in the meantime. E to power minus 1.8 divided by 0.02587. So we will get around 6 point into 10 to the minus 31. So it's in this order.
Gitanjali ma'am,
Yes.
actually I am taking the KVT value 0.025, and in that case the answer is uh, 5 point something into 10 to the power minus 32. So ma'am,
Okay. So let
actually
me,
they close to each other.
what? Can you please repeat your question?
Ma'am, actually I am using the value of KVT
Yes.
0.02, and
So,
if I am considering 0.025
yes.
KBT value, in that case
Hmm.
we got the option 5 point something into 10 to the power minus 32. So ma'am,
Yes.
actually we have to answer 6.14 into 10 to the power minus 32 and 6.14 into 10 to the power minus 13. Both are very close.
Yes. 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 Both are very close.
Yeah, ma'am.
So,
That's why.
okay. So there are two powers that are given in the answer. Means the two
Answer.
closed powers that is okay. So let
That's
me
why question is
contact with the NPTEL team regarding this question, regarding this question evaluation. Because if you are getting two answer, then we need to. So there is some error in the question. So let me contact with the NPTEL team. So we'll see. So it's
why
not
I
like
am asking.
yeah, yes.
That's why I am asking this you question number 8 because uh, I think the answer 6.14 into 10 to the power minus 34. 32.
Hmm. Yes, yes. Okay, I got your query. So there are two options that is very close to the answer. If you take 25 millielectron volt, then you will get around minus 32. And you will take if you take this 0.02587 or without any approximation, then you will get in the order of 10 to the minus 31, and these two orders are close. So let me,
Yeah.
I think there will be re-evaluation of this question, answer to this question. So we'll get the answer. So let me communicate and you will get your query. So you have already posted your question in the discussion forum.
My one friend posted this concern to the forum.
Okay, then, okay, let me contact with the NPTEL team, then we'll re-evaluate this question. So let us see what we can do with this question.
Thank you, ma'am.
Hmm. So other one, question number 6. So question number 6 is, it's like in thermal equilibrium state, the ratio of occupation probability of atoms in a non-degenerate atomic system in the ground state to the excited state is given by. So it's given it is in thermal equilibrium, so you can use the probability distribution that the number of atoms is proportional to U to power minus, let's say we are considering the ith energy level. So number of atoms in that energy level is directly proportional to U to power minus EI by KBT. Okay. So that means if we have two states, let's say N1 and N2, it's given there are two states and non-degenerate state, that means GI is 1. So what is the occupation probability of atoms in a non-degenerate state in the ground state to that of excited state? So it is asking about N1 by N2. So N1 by N2 will be U2 minus E1 by KBT divided by U2 minus E2 by KBT. So I think we'll get U2 uh, E2 E2 minus E1 by KBT. So if you look in the answer that is given in the question, so the second option, which is 1 by e to power E1 minus E2 by KBT. So this is the answer. You can write this in terms of this, right? So this is the answer. So is this clear to you? Is the solution? Bhargav, is this solution is clear to you?
आंसर तो ई के पावर माइनस ई वन बाई के बी टी होना चाहिए ना, तो अगर इसमें
What I
आंसर
didn't.
ऊपर करा ई के पावर माइनस ई वन फर्स्ट वाला फर्स्ट
हाँ,
ऑप्शन में, तो वो मैंने
फर्स्ट
किया था तो
ऑप्शन.
रॉन्ग थी।
सो फर्स्ट ऑप्शन अगर तुम देखोगे तो फर्स्ट ऑप्शन में क्या है? फर्स्ट ऑप्शन में है N1 by N2 is 1 by e to power minus of E1 minus E2 by KBT.
तो
So this is not correct, right? Like when you take this to the denominator, to the lower side, then you will get plus E1, not minus E1, right? So it is
Okay.
equal to so there is a sign error. I think you got confused in the sign.
Yes, ma'am. Yes.
Huh? Okay. Other than these two problems, does anyone have any other query regarding the solution of week 1 assignment and week 2 assignment? If you have any doubts regarding this week 1 and week 2, just write it the problem in the chat box. Otherwise, you can also unmute and tell you. I think I have unmuted all. So let me unmute. All. Assignment 2 question. Assignment 2 question. In a given two level, okay. So let us go through the 9th question. So it is saying in a given two level atomic system, the two level atomic system and ninth question. So there are two levels. Only lifetime broadening and collision broadening are present. If the lifetime of the level is 5 by 5 microseconds, so lifetime that means tau L is 5 by 5 microseconds. Okay. And the average time between two collision in the atomic system is 10 by 5 microseconds. So that means tau 0 is 10 by 5 microseconds. Then the total line width of the transition between two levels in terms of frequency. So you must have known when there are two broadening mechanisms. Then you can write the line broadening. That is the total line broadening delta nu as delta nu collision plus delta nu lifetime, right? So this is the final expression for when you have more than one line broadening mechanism. For collision, you must have known delta nu is it's half 1 by pi tau 0, and for lifetime it is 1 by 2 pi tau L. 1 by 2 pi tau L. So just take pi out, then it is 1 by tau 0 plus 1 by 2 tau L. So 1 by pi, so 1 by tau 0 is how much? It is 1 minute. So okay. So it is tau 0 is pi by 10, and this is 1 by 2 tau L. So that means it is pi by 10 also, right? 2 into 5. So we will get pi will cancel. So we will get 2 by 10. 2 by 10, and this is tau 0 in microsecond, right? So we'll get 10 to the 6 here. So it is 0.2 megahertz. What is the answer? It is 0.2 megahertz. So when you have more than one line broadening mechanism, let's say you have collision as well as you have lifetime. So to find out the line width, you can add these two terms individually. It's like collision happens because of some other events, and lifetime because of the lifetime of a level, like radiative and non-radiative transition. So you can add them up to find out the line width of the total response. Then you can use the whatever formula you have. For collision, it is 1 by tau 0, and for lifetime, it is 1 by 2 pi tau L. It's not like 1 by pi L, it is 1 by 2 pi tau L. So if you put now tau 0 and tau L are already given, just put it, then you can get the answer. So is it clear?
यस मैम, बट यहाँ पे मैं वहाँ पे मैंने देखा तो 1/2 पाई था मैम, कॉमन में कोलिजन में असाइनमेंट में, तो जो लेक्चर स्लाइड है
Collision
मैम
में तो okay, we'll go through the lecture slide today also, because I have not discussed the collision broadening in the last section. So we'll
ओके
see. It is 1 by pi 0, I think. Pi
यस मैम,
tau 0.
आई विल आल्सो थी, मैं भी देखता हूँ
Okay.
वैसे। ठीक
Okay.
है, ओके, थैंक यू मैम।
Hmm. Okay. So if you don't have any other queries for the assignment, so let me go through the uh, concept and whatever we are left with in the previous section. So we are discussing about the lifetime broadening, which is one type of homogeneous broadening. Okay. So in that case, what we have seen, the tau L, it is given by 1 by 2 pi tau L. Sorry, delta nu, that is the line width, is given by 1 by 2 pi tau L. And because of this finite lifetime of a level, what we'll see, so in a atomic system, usually we assume that the energy level are discrete, but it's not. In real situation, there is certain broadening in the energy level. So this broadening, it is due to the finite lifetime of a given level. So if you have if you have a line with delta nu, so what you will see, if you see this figure, E5, E4, E3, E2, then you will see there is a broadening of this energy level, so which is on the order of some nanometer. So this broadening, it is due to the finite line width or finite lifetime of a given level. So what we'll see, so during transition, so let's say the atom is making a transition from third level to second level. So in that case, because of this broadening, what will happen? So some atoms will make a transition from here to here. So let me take a given. So let me take a different color. So some atom will make a transition from here to here, and some will make a transition from here to here. So we'll see the atoms will interact with the radiation in other frequency also. And because of this, we'll see a broadening in the final spectrum. Like the emission and absorption spectrum, we'll see a broadening. Instead of a single peak, we'll see a broadening. So so if you want to find out what is the lifetime of this transition, so lifetime means how long it will last. So how long this transition will last. So for that, if you want to find the line width delta nu, so this is the summation of what is the lifetime of the second level. So this is delta nu second plus delta nu 3. So delta nu second, you already know, delta nu second level is 1 by 2 pi tau L2, and for the third level it is 1 by 2 pi tau L3. So if you put this expression here, so you will find what is the line width of a given transition. Okay. So from that, you can easily find out what is the lifetime of this transition. So which is 1 by tau equal to 1 by tau L2 plus 1 by tau L3. So in this way, you can find out what is the lifetime of a given transition. So this is all about one of the homogeneous broadening, which is lifetime broadening. So now let us discuss. So before that, let us go through two problems. Then we will discuss the collision broadening as well as the Doppler broadening. Okay. So the first question is, which one of the following process may involve non-radiative transition? So the the options are, first is spontaneous emission, second is stimulated emission, C is both spontaneous and stimulated emission, and D is none of these. So, and it is asking about which emission process involve non-radiative transition. So if you say stimulated emission, it occurs in the presence of a external pump. So this means whenever this transition occurs, stimulated emission occurs, so it always emit a radiation. So that means there is no non-radiative transition in the stimulated emission case. So that means only the spontaneous emission, it may involve the non-radiative transition. So it has two parts. One is the spontaneous emission has two parts. One is radiative as well as other one is non-radiative. So the answer will be A. So it's a problem based on the concept. So let us solve one numerical problem so that it will be helpful for you to understand the concept as well as to connect the concept. So the question number 2 is, if the coefficient of a stimulated emission for a particular transition is 2.1 into 10 to the power 19. So it is given the coefficient of the stimulated emission, which is nothing but B21. So if you consider two-level and two-level atomic system, so it is B21. So B21 is given, which is 2.1 into 10 to the power 19. And I am not writing the units. And the emitted is at wavelength 3000 angstrom. So when the atom is making a transition from second to first level, it is radiating one energy of wavelength 3000 angstrom. Now it is asking then the lifetime of the excited state. So coefficient of stimulated emission is given and the wavelength that is emitted during this transition is given. Now what you have to find out, you have to find out what is the lifetime of this excited state. That means what is the tau L or tau L for this excited state. Okay. So for this, what you can do, so you know that tau L, it is uh, related to the spontaneous emission coefficient, which is 1 by A. A21. So if you can find out A21, then you can easily find out what is the tau L for this system. So how you can find out A? A you can find out using the Einstein relation, which is A by B equal to 8 pi h nu q by CQ. So this relation you already know, right? From this relation, if you want to find out what is A21, then what you have to do? So you just have to rearrange the equation. So if you want to find out A21, then A21 is nothing but 8 pi h nu q B21 by CQ, right? And wavelength is given. So you can write the frequency in terms of wavelength as C by lambda. So if you put it here, what you can get. So in the next step, I have written the A in terms of the tau L. So A21 is nothing but 1 by tau L, and I have put the frequency expression, that is C by lambda, in this equation. So the final expression is this. Now to find out tau L, so this is nothing but CQ by 8 pi H nu Q B21. And nu Q is nothing but CQ by lambda Q. So we will get this expression for tau L. Now everything is given to you. Like lambda, you know, it is 3000 angstrom. H, you can take it as 6.6 into 10 to the minus 34. And please take care of the units. So everything must be in the same unit. Like you can't write H in the electron volt and take if B21 is given in watt, so you have to write H in terms of joule only. Okay, it's not like you take electron volt and watt here. So take care of the units, and if you put this expression like lambda is 3000 angstrom, B21 is 2.1 into 10 to the minus 19, 10 to the 19, and H is 6.6 into 10 to the minus 34. What you will get? You will get the tau L is 7.7 into 10 to the minus 8. So which is nothing but it is approximately equal to 80 nanosecond. So that means the tau L, that is the lifetime of this level, is 80 nanosecond. So the answer is C. Okay. So it is here you can see how you can relate different concept, like different relation with each other. Like tau L, it is related to lifetime broadening. To find out it, you can use the Einstein relation, which is 8 pi h nu q by cq. From that, you can easily find if one is given, one coefficient is given, then you can easily find out what is the value of other coefficient, and from that you can find out what is the lifetime. So these relations are correlated. So try to correlate this relation so that you can find out, you can relate the concept as well as you can find out the lifetime of different flavors. Okay, Nikhil, you are asking what will be the pattern of the exam. So exam, I think it's both subjective as well as it's not like everything will be MCQ type. So it's like you have to show the process. It's like this only. If you see this problem, how I solve it, it's like this. So you will be given some expression and you have to find out what is the value of this. Or I think I don't think they will ask derivation and all, but mostly they will ask about the problems or numericals that is related to the concept. So it won't be all numeric, all MCQ type. So there will be 5 marks, 10 marks question. Okay. So let us go through the second type of line broadening mechanism, which is the lifetime broadening, homogeneous and inhomogeneous broadening. We have already seen in the previous section. Like homogeneous broadening is the case where we have identical response from each of these atoms, and inhomogeneous we have non-identical response from each of these atoms. So in homogeneous broadening, we see the spectrum is centered around a single frequency, which is mu0. And in case of inhomogeneous broadening, we see there are different spectrum which are centered around different frequency. Other than mu0, we have response which is around lesser than the nu0 and higher than nu0. So that means the net response will be this red envelope. The net response is this red envelope. So for this case, we'll see what one of inhomogeneous broadening, which is Doppler broadening. So now let us. So this is all about the lifetime broadening that we have seen in the previous section. So I'm not going through this. So let us discuss what is collision broadening. So collision broadening occurs whenever there is a electric collision in the system. So it's not like the atoms are at rest. They do collide with other atoms whenever they are making a transition from higher energy level to the lower energy level. And because of this collision, we will see there is a broadening associated with it. So if you see, let us see atomic system. If you see the left figure, so if you see, 1 minute. So if you see this diagram, so it's a atomic system where atoms are, it consists of a collection of atoms. So now if you assume this atomic system is a two-level atomic system. So that means if you see this figure, it has two energy level. One is the ground state and another one is the higher energy, higher excited state, E2. Now, in this two energy level, if one atom, let's say one atom is making a transition from higher to lower energy state. Okay. So during this transition, what will happen? It will emit one radiation. And what is the spectrum of this radiation? It will be like this. So it will emit a radiation like this. So let me. Okay. So without any collision, what is the spectrum? The spectrum is like this. It's a perfect sinusoidal in all from minus infinity to plus infinity. But because of the collision, what will happen? There will be, so if you see this figure, the atom, this atom is colliding with, it's experiencing a two collision while making a transition. So if you see the red arrows, it while making the transition, it experiences two collision. So what will happen when it experiences two collision? So what will happen? That the phase of this emitted photon will get changed abruptly. So if you see this figure, okay, if you see this figure, then around this region and around this region, so there is a sudden change in phase. So it is because of the collision. So now we'll see how this phase change will affect the broadening in the system. Okay. So before deriving the collision broadening, so let us define some parameter that will help us to derive the equation. So one is tau zero. So tau zero is nothing but the average time between two collisions. So it's like one atom is here and it is emitting a photon and it is colliding one another photon in time tau c. So in between two collision, there is a time tau. So that means within this time, the phase will remain constant. And after this time, the phase will experience a sudden phase change. Okay. So this is the average time between two collision and the value, it depends on the pressure and temperature. And if you want to find out get an value of this tau zero, then it's typically lies between 10 to the minus 4 to 10 to the minus 10 seconds. And another is tau c. Tau c is nothing but the duration. It's the duration within which the collision lies, like the duration of the collision time. So it is always, the collision process is always instantaneous. So that means tau c, it's the order is typically in the order of 10 to the minus 13 seconds. So if you see the tau c is much less than tau zero. Okay. So that means the collision, whatever happening, it happening instantaneously. So in this collision process, during this instantaneous collision, we'll see there is a abrupt change in the phase. So how we can, so we'll follow the same process. So that means we'll first calculate what is the expression of electric field in the frequency domain. And by squaring it, we'll get what is intensity. And intensity is directly related to line step function. From line step function, you can easily find out what is the line width. Okay, so we'll follow the same procedure, whatever we have followed in the lifetime broadening case. So first, the electric field expression, which is Et equal to E0 e to power I 2 pi nu 0 t. Now this expression, so this is valid only between the collision time. That means from 0 to tau 0, this expression is valid because after this time, the phase will change. Okay. So that's why we are restricting the time period within 0 to tau 0. Okay. Now, if you want to, what is the expression of electric field in the frequency domain? You have to just take the Fourier transform of ET. So that means it is this expression, which is ET, e to power minus I 2 pi nu t dt. And the integration is from 0 to tau 0. So if you integrate it, it's a normal integration because there is only one variable t here and dt here. So if you integrate it and take the square, what you can found, you will find the line shape function is given by this expression, which is also Lorentzian. So in lifetime broadening, we also see a we also see that the line shape function is also Lorentzian. So in this case also collision broadening, the line shape function is also Lorentzian, which is given by g of nu is 2 tau 0 1 plus 4 pi square tau 0 square nu minus nu 0 whole square. Okay. And if you want to find out what is the maximum value, we have to put nu equal to nu 0, which is 2 tau 0. And from this, if g of nu 0 is 2 tau 0, you can easily find out what is the line width of this spectrum. Let's say we have g of nu as this. Then what you can do to find out the line width? So you just have to find out the value around the full width half maximum. So g of nu 0 around the full width half maximum is 2 tau 0 divided by 2, which is tau 0. And what you have to do, you have to equate it with this expression. Okay. So you have to put this is 2 tau 0 divided by 1 plus 4 pi square tau 0 square nu nu minus nu 0. So that means you can write it as, let's say, at half maximum, this this point is nu 1, and this point, the other point is nu 2. So you can write nu 1 minus nu 0 square. And nu 1 minus nu 0 nothing but delta nu by 2, right? So if you put all of this, you can find out what is the full width, line width of this g of nu, which is 1 by pi tau 0. Okay. So here you get the line width is 1 by pi tau 0, and it is not 1 by 2 pi tau 0. So for lifetime broadening, we got the line width is 1 by 2 pi tau L. But for collision broadening, it is 1 by pi tau 0. Okay. And if you put delta tau in g of nu, you will get the standard form of the line width function, g of nu. And this is the summary. Like if you have, like the problems we have discussed earlier, if you have two types of broadening mechanism, like one is lifetime broadening and another one is collision broadening, then you can, for the total response, you can write the line width as delta nu collision plus delta nu lifetime. Okay. So this is all about the homogeneous broadening. Now we'll discuss inhomogeneous broadening, where we'll see that the atoms, so there will be a spreading of the spectrum, and there will be response coming at different frequency. Other than nu 0, we'll get a peak around other frequency also. So Doppler broadening, like let's consider an atomic system where it consists of a collection of atoms, and it's a two-level system. Like it has two energy level E2 and E1, and the atomic resonance frequency is mu 0, which is E2 minus E1 by H. So now in this system, if let's say one atom is moving in the leftward and another atom is moving in the rightward direction, other unit. So one atom, if you see the atom is moving in this direction, or it can move in this direction, or it can move in this direction. this direction or diagonal direction. It can move in any direction because of the thermal fluctuation as well as because of the collision. So because of this, because of the different propagation direction, what we'll see that these atoms that are moving in different direction, they will experience different frequency. Okay, so let's say you are incidentating you are incidentating a radiation of frequency nu, but uh, um, 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 what will happen? So it will happen that these atoms that are propagating in different direction, they will experience frequency that is less than nu and that is greater than nu. So instead of experiencing this frequency nu, they will experience frequency that is less than nu and that is greater than nu. Okay, so it is because of the Doppler effect, which is given by this expression. So if you see this expression, Doppler effect, so nu days is nu 1 minus dz by c. So if you see, nu days is the frequency that is experienced, that is seen by the atoms, and nu is the frequency of the incoming radiation. So now in this expression, that is nu days is nu 1 minus Vz by c. So if you one atom is moving in the negative z direction, that means Vz is negative. So if you put negative Vz here, so what we'll get? This will be nu 1 plus Vz by c. So that means the frequency that this atom will experience is nu days, that is greater than nu. And similarly, you have atoms that is moving in the rightward direction, that is Vz is positive. For that case, what is nu dash? Nu dash will be nu 1 minus Vz by c. So it is less than nu. So here we can clearly see the different atoms that is moving in the different direction. They are experiencing different frequency of the incoming radiation. So because of this Doppler effect, we'll see there is a broadening in the system. So before going into the details of Doppler broadening, let us see what is the velocity distribution in the system. So the velocity distribution, it is given by Maxwell distribution, which is this expression rho v dv. So rho v dv is the probability that the atom has velocity between v to v plus dv. Okay, so this is given by this expression, and so this is the velocity distribution. Now, if you have this system where the atom is moving in this direction, so for that case, what we'll see, the atoms that is nu days, which is nu 1 plus Vz by c, that is moving in this direction, that is Vz is negative. So you know that the atomic resonance frequency is nu zero. That is, it's a two-level energy system, and the atomic resonance frequency is nu zero. That means the atom will interact only when the frequency is nu zero, because it is corresponding to the transition between two energy levels. So what will happen? The atom that has negative Vz. So this term is already positive. So to get nu zero, what this atom will experience now? If this nu is less than nu zero, then it is possible that this term will be, it is if the first term is less than nu zero and the second term is greater than nu zero, so we will get a frequency around nu zero. It's like compensation. So if it is moving in the negative z direction, then it will interact with the radiation which is frequency less than nu zero. And similarly, if it is moving in the positive direction, then it will interact with the radiation which is frequency greater than mu zero. Okay, so from that you will get a velocity distribution like this, which is shown in this figure. Okay, so this is the reason where mu z is less than 0, and this is the reason where mu z is positive. Now to find out what is the line width of a Doppler broadening, you can take the help of this Maxwell distribution, which is rho v dv is rho x dx, dx rho y dv dy, and rho z dz dz. So now we are considering only the z direction, that is the atom are moving in the z direction only. So that means the rho v dv is nothing but rho z vz, which is this expression. Now, as this is the probability distribution, that is, if you integrate it over all velocity, all possible velocity, then you will get a value of 1. So we will integrate it over all possible velocity, then you will get a 1. So just put this expression here and make a substitution. That is, make a variable change, that is Vz is nu minus nu 0 by nu z into C. Okay, so that you can get the what is the line width delta nu for the system. So if you do this substitution, what will, and another is change the limit. That is when Vz tends to infinity. So you know that the maximum velocity that the light can achieve, or any atom can achieve, is c, the velocity of light, right? So when Vz tends to infinity means Vz tends to c, and Vz tends to minus infinity is Vz tends to minus c. So from that case, we'll get the limit is nu tends to 2 nu 0 for Vz tends to infinity, and nu tends to 0 for Vz tends to minus c. Okay, so this is only the change in the variable. And in the next step, what we have done, we have changed the limit, because the velocity distribution, it is like a Gaussian distribution. So that means it is non-zero within a certain region, and it is zero in other region. Like if you see this region, it is zero, but around nu zero, it is non-zero. So for that, we can change the limit from 2 nu 0 to infinity. Okay. So in this uh, here we have only make a substitution of A is m by 2 pi kbt, m by 2 kbt, and change the limit from 0 to 2 nu 0 to 0 to infinity. So now if you compare this integration with the normalization condition of the line width, what we'll get? We'll get that for Doppler broadening, the line shape function, which is g of nu, you can write it as root over of b by pi exponential minus b nu by nu 0 square. So it's a, instead of a Lorentzian distribution, we are saying for Doppler broadening, it's a Gaussian distribution around the frequency nu equal to nu 0. So for homogeneous broadening, we see that the broadening distribution is like Lorentzian. But in case of inhomogeneous, which is Doppler broadening, we see the distribution is Gaussian. And if you want to find out the maximum value, you just have to put nu equal to nu 0. I think these two you can easily calculate. G of nu 0 is root over b by pi. And full width at half maximum is delta nu equal to 2 ln 2 by b square root. So if you see here also, the G of nu 0 is inversely proportional to the line width. Okay. So this is all about the Doppler broadening. And if you compare the Lorentzian function with Gaussian function, what we'll see? We'll see that the Lorentzian function is it's much narrower than the Gaussian distribution. So this is one of the comparison between the Gaussian and Lorentzian distribution. So for Lorentzian, if you see, the delta nu is 2 root over ln 2 by b. For Lorentzian, it is 1 by 2 pi tau l. In case of, if you consider the lifetime broadening, it is 1 by 2 pi tau l. Or if you consider the collision broadening, it is 1 by pi tau 0. And G of nu is this and this expression. So this is the comparison between the two functions. Now what we'll see next, this is, we have already covered what is homogeneous broadening, what is inhomogeneous broadening, and we have also discussed two examples of homogeneous broadening and one example of inhomogeneous broadening. Now we'll see how we can achieve the population inversion in a system. So we have already discussed what is the interaction of radiation with matter, what is the Einstein coefficient, what is the Einstein relation, what is atomic line shape function, and why we are seeing a broadening in the system. Now we'll discuss how we can achieve the population inversion in a system. So population inversion we'll see in the next slide that will achieve population inversion by pumping the system. Okay, by exciting the atoms in through a external pump. So for this, let's discuss. We'll discuss different types of pumping, like pumping in a 2-level system, 3-level system, 4-level system. Okay, so let us discuss the 2-level system first. So by 2-level, let's say we have one atomic system. So, and we already know that it's not like the atomic system has 2 energy levels. So there it is a number of discrete energy level, E1, E2, E3. Let's say it is E0, E1, E2, E3, E4, and E5. So it is multiple energy level in the system. Okay. So now in this system, if by 2-level we mean that only the two of this energy level will interact with the radiation. Like it may be so one energy level will be the ground state, and another energy level is one of this excited state. So if any one of this excited state and the ground state interact with the radiation, then we say that this system is 2-level system. Okay. So we can schematically represent this by this figure. So here the N1, this is E1 is the ground state, and E2 is the any one of this higher energy state, which is energy E2 and population N2, and this is N1. And in thermal equilibrium, what we have seen, we see the distribution of atom. It's like this. So this is energy, and this is the number of atoms. So we see that the atoms are mostly populated in the ground state, and as we move in the higher energy level, the population gradually decreases exponentially. So that means the N1 is much greater than N2 for all condition in thermal equilibrium. So it means we cannot achieve population inversion at thermal equilibrium in the 2-level system. Now, if we have a pump, which is H nu P, which is energy H nu P. So it's a pump. What it will do, it will excite some of the atoms from the ground state to the excited state. So what will happen? The number of atoms in the excited state will now increase, and it will and simultaneously the atoms will also make a transition to the lower energy level. So simultaneously there will be absorption and emission of the radiation. So we'll get a steady state population of N2 here and steady state population of N1 here. So in the presence of pumping, it is possible to increase the population of the higher excited state. So this is all about the 2-level system. Now if you see, so for the 3-level, 1 minute. Like so for the 3-level, so as we have discussed in the 2-level system, so what will happen in the 3-level system? So only the 3 energy level will interact with the radiation. So 3 level, one of the level will be the ground state, and the other 2 level will be the another higher excited state of the system. So if you see this figure here, so E1 is the energy of the ground state, E2 is the energy of the next excited state, and E3 is the energy of the next higher energy state. So if you consider the atomic population of ground state is N1, and for the next state is N2, and the next state is N3, and now we'll have a pumping in the system. So now if you excite the system through a external pump H nu P, what will happen? That atom will get excited to the higher energy state, which is E3, and after excitation, it may happen that it will make a transition from 3 to 1 directly by this transition, or it will happen that it will make a transition from 3 to 2 and 2 to 1. So it may follow the direct path or may follow the indirect path. And the next we will see that if in the indirect path, like from 3 to 1, 3 to 2 and 2 to 1, it is possible to achieve a population inversion in the system if the lifetime of the energy level are different. Okay. Depending on the relation between the lifetime, we will see that it is possible to achieve population inversion in the second level and the first level. So then we can achieve a lasing condition here. So we'll see in the details in the next few slides. Now let us see what is a 4-level system. So similar to 2 and 3 energy level, in the 4 level, only the 4 of the energy level will participate in the interaction process. So you can see there are 4 level, which is N1, N2, N3, and N4. In this 4 level, when we have a pump, so the atom will get excited to the higher energy level, which is this. And while de-excitation, so it may follow this direct path, or it may follow this path from 4 to 3, 3 to 2, or 2 to 1, or it may follow 4 to 2 or 2 to 1. So let me define this constant first. So omega p is the pumping rate of the system. What is the pump rate of the system? And T41 is the rate of transition, rate of the atomic transition from 4 to 1. 4-3 means rate of transition from 4 to 3. 4 to 2 means rate of transition from 4 to 2. So similarly, other terms also. Okay. And in this 4-level system, we'll see that under certain condition means under the lifetime of the different energy level, we can achieve a population inversion between the third energy level and the second energy level. So we'll see a lasing condition here. Okay. So this is the brief introduction to the 2-level system, 3-level energy system, and 4-level energy system. So don't get confused. The 2-level means only the system has 2 energy level. It's not like that. It's like only the among this discrete energy level, only 2 of this energy level interact with the radiation. So we say 2-level. And when 3 of these energy level interact with the radiation, 3-level system, and when the 4 energy level interact with the radiation or participate during the emission and absorption process, then we say it as a 4-level system. Okay, now we'll see the laser rate equation. So till now, do you have any doubts? Do any of you have any doubts? Okay, so let's move to the rate equation first. So a rate equation, it basically tells us about how the atomic population is varying with respect to time when we have a pump in the system. So previously what we have seen, when we have a thermal equilibrium condition, the population distribution is like this. So we see a exponential decay of the population when we move towards the higher energy level. So it means that the ground state is mostly populated, and as we move, the population gradually decreases exponentially. But in this is the thermal equilibrium condition. But now, if we consider a pump in the system, like external radiation in the system, what will happen? So the population, you can easily see in this figure, the population here, the population here, they are totally different. They do not follow any exponential decay. So this means that under pumping, it is possible to change the population of the system. And when we change the population in the system, we can achieve the population inversion and the Lessing condition. Okay, so it all depends on the lifetime of the system. So before discussing the rate equation, so let us see one new term, which is photon flux. So this is mostly used to rewrite the rate equation. So it is only redefining the equation. It is nothing new. Okay. So previously we have seen the Einstein relation A by B is 8 by h nu q, C by n q. And A is given by 1 by TSP, and you know which is the spectral energy density is given by I nu by C by n. Using this relation, we found that the rate for stimulated emission from 2 to 1, it is given by W21 N2, where W21 is nothing but B u nu G of nu. And if you put the value of B u nu and B and u nu in this case, will get this expression. And in this expression, if you rewrite it, you can write it in terms of this scattering cross section, which is sigma nu. This we have already seen in the previous section, sigma nu. Okay. So you can write it in terms of sigma nu, I nu by h nu, and n2. And the I nu by h nu in this case, it is nothing but the number of photons per unit time per unit area. So this indicate the photon flux. Okay, how many number of atom is crossing the cross section per unit time per unit area. So this is the photon flux. So now you can write the rate equation as gamma 21 is sigma nu phi nu n2, where omega 21 is cross section multiplied by photon flux. Okay, so this is the expression. Now if you write the rate equation for the two level energy system, what we have? So for this two level energy, two level system, you have two energy level. One is population N1, and another one is population N2. Okay. So in this case, if let's say we have a pump, H nu P in the case. So if we have a pump, so what will happen? So the atom will get excited to the higher energy level, and during de-excitation, what will happen? There will be spontaneous emission as well as stimulated emission. So for spontaneous emission, what we have? For stimulated absorption, like the excitation of atom from lower energy level to the higher energy level, we have the rate equation is omega 1 to n1. And for the stimulated emission, we have omega 21 n2, and for the spontaneous emission, we have T21 n2, right? So this is the different process that can happen during the pumping. Now, if you want to find out how this population of this higher energy state is changing with respect to time, so dN2 by dt, you can write it in terms of this. So that means the number N2 will increase whenever we have absorption in the case, which is omega p n1, and it will decrease by stimulated emission, which is omega p n2, and by spontaneous emission, which is T21 n2. So this stimulated absorption will increase the N2 population and the emission will decrease the population. So this is the final rate equation. So now if you want to find out what is the how the population of the first excited state is changing with respect to time, what you can do. So the stimulated for this first excited state, what are the process? The processes are absorption and two emission. So the emission now will increase the population of the first excited state, so the ground state, because it is the atom are now moving from the second level to the first level. So it will increase the population. So that is what written here. So omega p N2 is the stimulated emission and rate of stimulated emission, and T21 N2 is the rate of spontaneous emission. So these two will increase the population of the first excited state, the ground state N1. Now the absorption process which is happening from 1 to 2, which is this process will decrease the N1 population. So that's why we have a negative term here, which is minus omega p N1. Okay. So now you can easily see dN1 by dt is negative of dN2 by dt. So now if we have a steady state, so steady state, the number of atoms in both of this level will remain constant. So that is why we have dN1 by dt equal to 0 and dN2 by dt equal to 0. So this is the steady state condition. Okay. So now if you put it here, if you put this condition here, what we will get? We have dN2 by dN2 by dt equal to 0. So that means omega p N1 minus omega p N2 minus T21 N2 is 0. So from this we can easily find out what is how N2 is related to with N1. So we will get N2 omega p plus T21 equal to N1 omega p. So that means N2 by N1 will get omega p divided by omega p plus T21. So here if you see this omega p, T21, they are all positive. So that means this N2 by N1, it is omega p divided by omega p plus T21. So that means this term is greater than the numerator term. So that means this N2 by N1 is less than 1. So N1 is always greater than N2 in the two-level energy, two-level system. So this means that if for any pumping rate, even if we increase the pumping rate, we can't achieve the population inversion in a two-level system. Okay. So this is one of the conclusion that you can achieve. Now we'll see. So previously you must remember we have taken delta nu as I think N0. So we have approximated as 1 plus I nu by Is. This we have assumed, we have taken in our previous section. So now we'll see how we can derive this relation. So if you take, so delta n is nothing but N2 by N1, right? N2 by N1, so we have taken a ratio N2 by N1 divided by N2 plus N1. So if you now divide both numerator and denominator by N1, so we'll get N2 by N1 minus 1 and N2 by N1 plus 1. Okay. And what you have to do, you have to put this expression here. You put it, we'll get a final expression like minus of T21 divided by 2 omega p plus T21, which is nothing but delta n by n. I think these are simple, so you can easily understand what these expressions are. So now if you make rearrangement, you will get delta n is minus of T21 divided by 2 omega p plus T21 n. Okay. So previously we have derived the gain coefficient as in terms of these absorption cross section or cross section of the system and multiplied by delta n. And this delta n, if you put this delta n here, then you find that this is nothing but minus of sigma nu T21 divided by 2 omega p plus T21 n. So this minus of this term, you can write it as minus of alpha nu. So alpha nu is nothing but the absorption coefficient. So it is in negative term. So this it is negative of gain. So that means it is related to the absorption in the system. Okay. So alpha nu is this expression. Please go through this expression. Okay. So alpha nu is nothing but the absorption coefficient. And in this expression, what you can do for this second term, which is 2 WP tau L, you can write it in terms of, you can put the value of omega p as sigma nu, I nu by H nu. So omega p, you already know it is sigma into flux, right? And sigma into flux is nothing but I nu by H nu. So this, you can make this substitution here. And other than I nu, you can take other constant as Is. So Is is the saturation intensity that we have seen earlier. Okay. So that means you can write it as I nu by Is, which is nothing but the saturation intensity. So this is the final expression, the absorption coefficient. So similarly, for gamma nu, for gain coefficient, we have got expression gamma 0 nu 1 plus I nu by Is. Similarly, for alpha nu, absorption coefficient, we have expression alpha 0 nu 1 plus I nu by Is. Okay. And alpha 0 is the similar to the small signal gain coefficient. We have small signal absorption coefficient here. And if you plot this expression, you get a similar plot which is similar to the gain coefficient curve. So you see that when I nu is much less than Is, then alpha nu can be taken as alpha 0 nu, which is small signal gain coefficient. So in this region, the alpha is mostly constant. But when I nu gradually increases, we'll see it, the absorption gradually decreases. Okay, it decreases like this. And what is the application of this at this? So we'll see one important application of this absorption coefficient. So for materials which have small values of Is and a value of alpha 0 nu, we call that material as saturable absorber. Okay, small value of Is and large value of alpha 0. So we will get a curve like this. So if you see, so after this we'll discuss two problems, I think. Then we'll discuss what is three-level system. No, we'll discuss three-level first, then we'll solve a few problems related to this concept. So saturable absorbers are those which have small values of Is and a large value of alpha 0 nu. So if you see it, so this is the curve for saturable absorber. So what will happen when we have a material like this in the system? So what will happen? So we'll see that in this region, the light will get transmitted. But in this region, the light will be completely blocked. So that means for I nu much less than ISA, the light will be absorbed by the system. And for I nu much greater than IS, it will pass through the system. So what is the application? The application is we can use it for pulse cleaning. Okay. So let's say we have a system. So generally we assume that the pulse is like this, the incoming pulse is like this, but it's not in reality. It's like there are noises in the system, in the pulse. Like we will see there are noises in the pulse. So we will see there are noises, and for particular application, these noises are really detrimental. So how we can remove the noises? So you can remove the noises by using the saturable absorber. So this is what shown in this schematic. So if you see the schematic, so there is a saturable absorber here and there is a incoming pulse. So in this output, what will happen? So let's say the pulse have frequency noises in this region. Okay. So this is the absorption coefficient plot for the saturable absorber. So what we'll see beyond IST, the light will pass. So the pulse will pass through the system. But below IST, in this region, we'll see that there is a absorption in the system. So the intensity will be absorbed by the saturable absorber. So this is what shown in this figure. Okay. So if I take other color. So this is the level for IST. So that means below that it will be absorbed, above it will pass. So what we'll see in the output, we'll see the pulses. The output pulse will be like this. So in this way we can clean the pulse. So that means we can remove the noises in the system using the saturable absorber. So this is one of the application of saturable absorber. Other application are that we'll see in the next in the few in our upcoming live section, that we can use it for Q switching and passive mode locking. So this is all about the two-level system, the pumping in the two-level system and the rate equation in the two-level system. So do you have till now, do you have any doubts for the two-level system? Otherwise, we'll discuss the next one, which is three-level system. We'll discuss its rate equation as well as we'll discuss few problems. I think 3 and 4 problems we'll discuss it. 4 problems actually. Then we'll move to 4-level system. So is there any doubts till now? So if not, let us move to the 3-level system. Okay. So similar to the 2-level system, in 3-level system, we have 3 energy level that is interacting with the radiation. That is the absorption as well as the emission. It is occurring between 3 energy level. So if you see this figure, there are 3 energy level. One is atomic population N1, N2, and N3. So now if you have a pump in the system which is H nu P, what will happen? The atom in the ground state will get excited to the higher energy state, and during de-excitation, it may follow the direct path, that is from path to 3 to 1, or it can follow the indirect path, which is 3 to 2 and 2 to 1. So in this system, one of the example of this 3-level system is Ruby laser. So Ruby laser we'll discuss in detail in our next section. So for now, let me give you a brief introduction. So for Ruby laser, so it is it can interact with 2 pumps, like one which is around green and one is around blue light. Okay. So if you are incidenting a green laser radiation, what will happen? It will excited to the 4F2 state. And if a blue, then it it will get excited to the next energy band, which is 4F1. Okay, so depending on the pumping type of pumping, it will get excited to one of this state. And during de-excitation, what happens? It comes down to one of the intermediate state, which is R1 and R2. So R1 and R2, if you see the lifetime, it is 3 milliseconds, and it is also termed as a metastable state. That is, metastable state means the state where the atom stays for some time. So it is metastable state. So what happens when you pump the system? It immediately goes to this R1 and R2 state, and after, depending on the lifetime, we'll see a laser action in this R1, R2, and the ground state. So this and the laser will get is around 694 nanometer, which is around red color. Okay, so this is the dominant contribution. And another type of radiation that we can get is 693 nanometer. So this Ruby laser, it's a typical 3-level system. And if you want to represent it schematically, so this is what is the representation of a 3-level system. This we have already seen in the previous slide also. So we have 3 energy level, E1, E2, and E3. And when we have a pump, the atom get excited to this state, and it through this metastable state, it get populated in the E2 state, and we see a laser action in the second state and first state. Okay, now let us see the rate equation, how the rates are related, how the atoms are changing in this energy level. So if you see the 3-level atomic system, let us consider the 3rd level first. So the highest state, which is interacting with the radiation. So for this highest state, what is the process that is how this N3 will increase? So the N3 will increase whenever there is a stimulated absorption, right? That is WPN1. So this will increase the population of this system. And how the N3 will decrease? N3 will decrease by stimulated emission through this direct process, or spontaneous emission through this direct process, or it will decrease through this spontaneous emission to the E2 level. So I have already, I think, defined this term. So omega P is nothing but the pumping rate. Omega P is the pumping rate. And Tij, so Tij is the rate of the transition from I to J. So rate of transition from I to J. So for N3, what will happen? This omega P N1 is nothing but the stimulated absorption, which will increase the population, and omega P N3 is the stimulated emission. T32 and 3 is nothing but it is this process. It is this radiation. That's the spontaneous emission from 3 to 2. So this will decrease the N3 population, and T31 and 3 is the spontaneous emission from 3 to 1. So this is for how the population of the 3rd level is changing with respect to time. For N2, for the 2nd level, we see that the 2nd level population will increase through this process, which is T32 and 3. T32 and 3, and it will decrease by the spontaneous emission as well as stimulated emission. So spontaneous emission is nothing but N2 T21, and the stimulated emission is WLN2. So WLN2 is the stimulated emission from this case, from this 2 to 1. And the stimulated absorption from this from 1 to 2 will increase the population. So that's why we have a positive WNN1 here. Okay, so this is how the population of the 1st level the N2 level is changing with respect to time. And for dn1 by dt, what you can do, you can find out from these processes also. Otherwise, you already know n is n1 plus n2 plus n3. So dn by dt equal to dn1 by dt plus dn2 by dt plus dn3 by dt. dn by dt is, it is always 0 because the total number of atoms is always constant all the time. So that means this is 0. From this, you can find out what is dn1 by dt in terms of dn2 by dt and dn3 by dt. So if you find it, you will get a same expression like this. Okay. So this is the rate equation for the first, second, and third energy level. Now, if you consider a steady state, so for steady state, what we have? We have dn3 by dt equal to 0, dn2 by dt equal to 0, and dn1 by dt equal to 0. So we have this condition. So now you just have to put this steady state condition in this expression. Okay. If you take first equation, which is equation 1, what will get? You get this form. From this, you can find out what is the ratio of the atomic population of N3 with respect to N1. Okay, which is omega p divided by omega p plus T31 plus T32. Similarly, if you take the second equation here, what you will get? You will get this, which is dn2. So we will get a final expression this. So this is a simple algebraic equation. You just have to rearrange the terms and get the ratio. So n2 by n1 will get wl divided by wl plus t21 plus this term. Okay. Now if you want to write it in terms of total n, so total n is nothing but n1 plus n2 plus n3. So take n1 common in this equation. So we'll get n1 is n divided by this term. So that means if you want to find out delta n by n is nothing but n2 by n1 divided by n1. So delta n is n2 by n2 minus n1. Now what you have to do, we have to put this expression, this 2 and 3. Use this equation and put it in the delta n. So you will get this expression. Wait, this is the final expression for the delta n for this 3-level system. Now, if you take one value for this time, lifetime. So if you take normally T3, T32, it normally lies between 10 to the power 8 to 10 to the power 10, so 10 to the power 9 second invert. And if you see T31, it typically lies in 10 to the power 6 order. And T21 is 10 to the power 2 to 10 to the power 4 order. Here you can easily see the value of T21. It is much less than both T31 and T32. Okay, so that means we can make an approximation here. Like we can take T32 as much greater than T31. Okay, if we take T32 much greater than T31, so we can neglect the term here T31 here. So what we'll find? We'll find delta n is this. So that means if you have equation 4, so in equation 4, if we want to have population inversion in the second and first level, so the delta n should be greater than 0. So that means this term, this should be positive, right? So this term should be positive. So this is what written here. So for this term to be positive, what we have? This negative term, this minus term should be positive. So that means for population inversion, what we have T32 must be greater than T21. So that means if you see the schematic, T32 is from, so let me erase it. So T32 is from here to here, 32 to 3 to 2, and 21 is from this level to, from second level to the first level. So for spontaneous, so for stimulated, for the population inversion, we need to have, we need to have T32. The rate of from 3 to 2 transition must be greater than the rate from 2 to 1 transition. So this condition must be satisfied to have population inversion. Okay, so this is what written here. T32 must be greater than T21. So now you can also make, you can simplify this expression 4 by using this approximation. If you use it, you found that this delta n by n can be written as equation 5. And to have gain, now in this system, if you want to have gain, so let's say we have a system where both T32 is greater than T31. So this is the first approximation we have made. The second approximation we made is T32 is greater than T21. So these are, let's say we have both these conditions satisfied. So now what we have delta n divided by ns, this equation 5. Okay. Now for this case, for n2 to be greater than n1, what we have? We have omega p also greater than T21. So we have now one additional condition, that is omega p must be greater than T21. So if these three conditions are satisfied, then we have population inversion in the system. Okay. And threshold is the case where we have n2 minus n1 is 0. So for this case, what we have? Omega pt, that is the threshold value of pumping power, is T21. So threshold means after, if we increase the pumping rate beyond this point, if we increase it, then we'll see a population inversion. So that's why T21 is the threshold value. So if you want to find out the threshold pumping rate, you just have to find out what is the T21 for this system. So once you get the T21 value, you can get what is the minimum value of pumping rate that is required to see the lasing condition in the system. So this is what summarized in this figure. So if you see this figure, so there is a pumping WP from 1 to 3, and T32 is first. That means T32 is greater than what is that? T2, T31. So it is first means T32 is greater than T31. And there is this T21 is slower than T32. So we will see a lasing condition here in the n2 and n1 level. Okay. Now let's see how in this 3-level system we can get this gain saturation. So for 2-level, we initially see we can represent gain as gamma 0 nu divided by 1 plus I nu by Is. And for this 3-level, let's see how we can represent the gain saturation. So this is the expression, final expression we got, equation 5. So in this, if you divide it by omega p plus T21, what we get? We get that this term plus this term and this term. So if you see this term, this third term, this is T21 in the numerator and T32 in the denominator. So T21 is less, it is a negligible value because T32 is much greater than T21. So that means this value is negligible compared to the first term. So that's why we neglected the second term, the third term. So if you neglect it, you got a expression like this. And from this, I think you can represent this in terms of, so if you just need to put the value of omega L, and other than I knew, you just represent the other constant as Is. So if you put it, you can get this expression delta n is delta n0 1 plus I know by Is. Okay. And delta n0 is this value. And for similarly for the gain curve, you see a curve like this. So it's a curve like this. So for I nu much less than Is, we have small signal gain coefficient. And as the intensity increases, the gain gradually decreases in the system. So if you see the curve, let's see what is the intensity profile when we have a weak signal input, that is I nu is much less than Is. So when I nu is much less than Is, what is gamma nu? Gamma nu is nothing but gamma 0 1 plus I nu by Is. This you can write it as gamma 0, right? I nu by Is is it's a negligible term because I nu is much less than Is. So for this we have I nu as this I0 e to power gamma 0 z. So that means the intensity will increase exponentially in the system when we have intensity that is much less than the saturation intensity. Now, if instead of this we have I nu, which is comparable or which is greater than Is. So for that case, what will happen? Initially, there is a exponential increment because for this case, I nu is much less than Is. So gamma 0, you can take gamma as gamma 0. So this will increase. Then after some time, what will happen? Because you have already seen the gamma varies like this. It decreases as we increase the intensity. So that means there will be, so now the this exponential increment will decrease and will gradually we'll see a constant value here. It will remain constant after this time. Okay, so these are the intensity profile under different conditions. One is where intensity is much lesser than the saturation intensity, and the other case is the where the intensity is it is comparable to the saturation intensity as well as it is greater than saturation intensity. So these, I think these are equal. These two slats are same, I think. Yes, these two slats are same. So now let us discuss few problems based on this rate equation. So first problem is, consider the energy level diagram shown below, which correspond to the molecular nitrogen level laser. So we have a nitrogen laser. So if you see the diagram, it is a 3-level system. Now in this system, if the pump rate R is 10 to the 20 atoms per centimeter cube per second, and the decay roots are is shown with tau 21 is 20 nanosecond and tau 1 is 1 microsecond. Okay. Then the equilibrium population of states 2 and 1 are respectively. So you are given a 3-level system, and you are given what is the pumping rate and what are the value of a lifetime of this 2 to 1 transition and lifetime of 1 to 0 transition. Now it is asking about what is the equilibrium population state of 2 and 1. So after whenever there is a pumping, after some time it will achieve a equilibrium position. So we will have a N2 number of atoms here, N1 number of atoms here, and N0 number of atoms here. And it is asking about what are the values of N2 and N1. So how you can solve it? So to solve this problem, what you can use the condition of equilibrium. So at equilibrium, the rates are zero, like dN2 by dt is zero and dN1 by dt is zero. And dN2 by dt, if you see, so let us see the process. So there is a stimulated absorption from 0 to, let me use a different color. So there is a stimulated absorption from 0 to 2, and there is an emission which is occurring from 2 to 1 and from 1 to 0. Now, if you want to find out what is the rate at which N2 is varying, so dN2 by dt is nothing but R minus the emission. So absorption process will increase the population and emission process will decrease the population in second level. So that's why I have written R minus N2 by tau to 1. Okay. Similarly, for first level, what will happen? The transition from 2 to 1 will increase the population. So that's why we have N2 divided by tau to 1 here. And the emission process that is from 1 to 0, it will decrease the population. So that is why we have minus of N1 by tau 1 here. And this R is given, tau to 1 is given, tau 1 is also given. Now we'll put the equilibrium condition, that is dN2 by dt equal to 0. If you put it, what you will get? You will get N2 is R times tau to 1. So that means you just put the value of R and tau to 1. So we'll get what is the equilibrium population of the second level, right? And for the first level, what you have dN1 by dt is 0. So that means N1 is tau 1 divided by tau to 1 N2. And N2 by tau to 1 is nothing but R. So this means tau 1 into R. So R is given, tau 1 is given. You just find out what is the population of N1, which is 10 to the 14 per centimeter cube. So this is how you can find out what is the population of equilibrium population of the level 2 and 1. So is this problem clear to you? If it is clear, then we can move to the next problem. Otherwise, you can ask the doubt if you have any query in any one of these steps. If any one of these step is not clear to you, then please ask the doubt. Do you have doubt in this problem? Okay, so let's move to the next. So please remember how you are solving the problem, because it's not like this will be asked, but it may help to solve some other problems also. Okay. So the second question is a conceptual one. So it is, it's like this. So it is the question is, to sustain lasing action in a 3-level laser as shown in this figure, the necessary condition is or are. So you have 3-level laser 210, and there is a population inversion, sorry, there is a lacing condition in if 2 to 1. So what are the conditions that is required for lacing action in this 1 to 0 or energy level? So let us see the options. The first option is lifetime of energy level 1 should be greater than energy level 2. So this is true because we have seen in this if the lifetime of this level is greater than this level, then the atoms will rapidly decay to this state. Okay, so this is true. It is required for the lacing action. And the second one is population in level 1 should be greater than 0, level 0. So that means the population, that is N1, should be greater than N0, which is also the case. For population inversion, you require that N1 should be greater than N0. So that means this is also correct. And the third is population in level 2 should be greater than level 1. So this is not the case. For population inversion, what we need, population here should be greater than the population here. So this is not the case. And the D option is all of this, which is also not the case. So that means the answers are these two options. Lifetime of energy level 1 should be greater than energy level 2. And population in level 1 should be greater than level 0. So this is conceptual based. Let us move to the next problem. So the next one is consider the atomic system is shown in the figure, where Einstein A coefficient for spontaneous emission for the levels A21 is this and A120 is this. And if 10 to the power 14 atoms per centimeter cube are excited from level 0 to level 2. So we are exciting this many number of atoms per unit volume from level 0 to 2. That is from here to here. From 0 to 2. And a steady state population in level 2 is achieved. Now it is asking about then the steady state population at level 1 will be x into 10 to the power 13 per centimeter cube. Then it is asking about what is the value of x in this problem. So let us see what is given to us. So it is given A21, that is this process A21, and it is given A10. So if you see, these two are given and N2 is also given. It is 10 to the power 14 atom per centimeter cube. And it is asking about the steady state population of level 1. So if you write dN1 by dt, so if it is in the problem, it is asking about the steady state population, equilibrium population, then start from here, start from the rate equation. So dN1 by dt is, it will increase when we have transition from 2 to 1. So this is nothing but N2 A21, and N1 will decrease when we have transition from 1 to 0, which is nothing but minus of A10 N1, right? And at steady state, what we have? We have dN1 by dt is 0. So from this, we can write N1 is N2 A21 by A10. So this means N2 is given, A21 is given, A10 is given. So that means N1 is, if you calculate it, you will get, it is 2 into 10 to the power 13. So which is nothing but the integer x will be 2 here. Okay. I think this is also easy. If you know the rate equation and if you know what is steady state condition, then you can easily find out the equilibrium condition, equilibrium population. So this is all about the 3-level system. It's almost time, so let's discuss the 4-level system in our next section. And till now, do you have any doubts in any problem or in any concept or in the assignment also? So let's clarify your doubts and end the section. Till now, whatever I have told you or whatever the problems I have solved, is it clear to you? Or do you have any doubts in any of this concept? So today we talked about what is two-level system, what is three-level system, and what is the rate equation in the presence of a pumping. So when you have an external pump, how the rate equation will get affected. So we studied about all this. Also, we studied about Doppler broadening, collision broadening, which where Doppler broadening is one type of inhomogeneous broadening, and collision broadening is the homogeneous broadening. So we discussed that. We discussed two-level, three-level system. So in this concept, do you have any doubts? Bhargav, I think you can hear me. If you don't have any doubt, then let's end this section for now. Then we'll discuss the four-level system as well as the week 4 content in the next section.
मैम इसका स्लाइड वीक 3 का अभी तक तो नहीं मिला है, अपलोड नहीं हुआ।
हाँ वीक 3 का नहीं हुआ है, बट आई थिंक मैंने जो गूगल ड्राइव बनाया है इस कोर्सेज के लिए, दिस इज विजिबल टू यू राइट, द गूगल ड्राइव लिंक where I upload the this file. So today I will upload the week 3 content there, so you can see that from that folder.
ओके
Okay. Any other doubt?
नो मैम।
Okay. So okay, let's end the section now. So thank you for joining the section. So I think whatever I have discussed, it is clear to you. Otherwise, we'll meet on next Saturday from 4 to 6, same time. So let's end the section now. Okay, bye. Let's meet on next Saturday.